Hello friends, I am Aher from RBNB College, Rampur. I am from Physics Department. Today we study the chapter Superposition of Waves. In this chapter, we study the free vibration and force vibration. For free vibration, we consider a simple pendulum. Example of simple pendulum. What is the free vibration? See, consider the simple pendulum. In this simple pendulum, this is the rigid support, this is the equilibrium position. If this simple pendulum displaces through some distance, it performs the vibration. Now, as time increases, the vibration, the amplitude of vibration decreases, and this type of vibrations are called as free vibration. Therefore, we define free vibration as the body is said to be perform free vibration when it is displaced from equilibrium position and there is a vibration. The vibrations are displayed, there is a loss of energy and the amplitude of vibration decreases as time increases. Such a type of vibrations are called as free vibration. Now, there are different examples of free vibration. A vibration of simple pendulum, vibration of tuning fork, vibration in or the oscillation of current in LCR circuit. These are the examples of free vibration. Now, forced vibration. Forced vibrations are the different from the free vibration. The forced vibrations are the vibrations are produced by the external periodic force. In force vibration, an external periodic force is applied to the body whose vibrations are different from the natural frequency and whose natural frequency is different from the frequency of external periodic force. For example, we consider the compound pendulum. Due to one pendulum natural frequency, the energy is transferred to the another pendulum and another pendulum is also start to the vibration. Such a type of vibrations are the force vibrations. Now, suppose we apply the cell to the clock, such a type of vibrations are also force vibration. These are the force vibration and free vibration. Now we see the end correction. End correction, here we consider a jar containing the water and a tuning fork held near the open end. Near the open end, when it is hammered, the wave, longitudinal wave sent through this pipe and the longitudinal wave sends the wave, it is reflected from this closed surface. There is node formed at the close end and antinode is formed at open end. Now, this antinode, it is not exactly at the open end, it is little distance above the open end and it is called as end correction. The end correction is represented by E. End correction is represented by E. See, the tuning fork hammer and tuning fork produces or sends a longitudinal wave. The longitudinal wave travels through this pipe and it is reflected back from this close end. At close end, node is formed, at open end, antinode is formed. This antinode, it not formed at a exact open end, it is little distance above the open end and this distance, it is called as end correction. This end correction is represented by E and end correction is given by 0.3 D, where D is inner diameter of the tube. Inner diameter of the tube, then the corrected length, see, L is equal to, this is the length of air column, this is the length of air column, L is the length of air column here, L the corrected length is L plus 0.3d, where this is the corrected length, L is the length of this air column, 0.3d is the end correction. Now here we study the end correction for two cases. First, we consider pipe closed at one end. Here pipe closed at one end. See in figure A, pipe is closed at one end if the tuning fork, vibrating tuning fork held near this pipe, the wave is sent, that is longitudinal wave sent through this pipe, and suppose this is the incident wave. This is the denser medium, this is here rarer medium. The wave is reflected back, interfere with each other, forming a stationary wave. This is the stationary wave here. Now in this case there is again the node at the close end and antinode it is at the open end, and in such a case the antinode it is not exactly formed at open end, it is little distance above the open end. Here there is a one end correction and it is 0.3d, it is 0.3d. That is, when the pipe closed at one end, there is one end correction and which is given by 0.3d, where d is inner diameter of the tube. Now in second case we consider pipe open at both ends. In this case, see, pipe is open at both ends, and now by our boundary condition, antinode is formed at open end. That is, there is antinode at the open end and node is at the center. Now here in the figure B, see there are two antinode, one node. The pipe is open at both ends. Therefore, there is one end correction here and one end correction here. There is two end correction, and we can say that corrected length is L is equal to length of air column. L is the length of air column plus 2E. Here the corrected length is equal to, this is the length of air column L, and there is only one end correction, therefore it is plus E. Now L is equal to, we can write corrected length is equal to L plus 0.3d here, and L is equal to corrected length L plus 0.6d in case of pipe open at both end. Now we see the vibration of air column in a pipe closed at one end. Now we draw the figure. In this figure we consider the three conditions or three figures. This is the first fundamental mode. The pipe is closed at one end. Now in next case it is also having same length. Pipe is closed at one end, and again there is third mode of vibration. The pipe is closed at one end. We consider three modes of vibration here. Now vibration of air column in a pipe closed at one end. See in this figure, in each figure there is a pipe is closed at one end. Now this is the first, it is the fundamental mode, it is the lowest mode, fundamental mode. In figure A, see the in fundamental mode, the vibrating tuning fork held near to this pipe open end of the pipe. Here we neglect the end correction, and the wave is sent, longitudinal wave sent through the air column. It is reflected back and interfere with each other, forming a stationary wave. Now at close end there is a node, and at open end there is antinode. Now this is the length of air column. Now see, in next figure, in first figure here, we consider this is the lowest mode of vibration. It is called as fundamental mode. See in this figure A. In figure A, L is the length of vibrating column. L is length of vibrating column. The corrected length is equal to, now in this case pipe is closed at one end, there is only one end correction, therefore corrected length is L plus E. There is only one end correction. Now see, this is the length, it is called as length of air column. Length of air column is equal to length of air column is equal to, now we see the mechanism of this node and antinode. If vibrating tuning fork held near to the open end of the pipe, the compression it is sent by this tuning fork. Now this is the rarer medium, this is the denser medium. Now the compression is produced here, this compression is travel here, again there is a reflection, and this is reflected back, and there is again rarefaction. Here the rarefaction is reflected as a compression. Now at the open end antinode is formed, at the close end node is formed. There is a boundary condition. The node is formed at close end and antinode is formed at open end. Now the corrected length is L is equal to L plus E, then length of air column. Now here we consider N is the fundamental frequency, lambda is the wavelength. Now in this case length of air column is equal to, this is distance. We can say that this is the distance between node and adjacent antinode. Now length of air column is equal to distance between adjacent node and antinode. We know by the properties of the stationary wave, the length of air column, it is equal to here distance between node and antinode, it is equal to lambda by 4. Therefore L is the length of air column and distance between node and antinode is lambda by 4. Therefore lambda is equal to 4L. We can write the corrected length, that is lambda is equal to here 4L, capital L, that is we can say here L, it is L plus E. It is the 4L. Now we have the frequency. V is equal to, V is velocity, N is the frequency, lambda is the wavelength. This is the basic formula for velocity. V is equal to N lambda. N is equal to V upon lambda. Substitute the value of lambda here. N is equal to V upon lambda is equal to 4L. This is equation number 1, and which is called as fundamental frequency or lowest frequency. It is called as fundamental frequency. It is also called as first harmonic. It is also called as frequency of first harmonic. First harmonic. See, in fundamental mode of this vibration, n is equal to V upon 4L. We can also write that is this n is equal to V upon 4 into L plus E also. Now n is equal to V upon 4L. This is the frequency of fundamental mode. It is called as fundamental frequency or frequency of first harmonic. Now in figure B, there is a second mode, or we can say in this mode we consider here and we know there is antinode at the close end and node is at close end and antinode is at open end. Now here we consider such a type of, this is the incident wave and it is reflected, the reflected wave, it is like this. This is, see, this is node here, this is node and this is the antinode. This is also antinode. It is called as, in this figure B shows the second mode of the vibration. This is the length of air column. In this, the node is formed at close end and antinode is formed at open end. In the second mode, there are two antinode, two nodes. Now in this case, see, the frequency, the mode consists of the frequency n1 and wavelength lambda 1. Then length of air column, length of air column, length of air column is equal to distance between, the distance between these node, antinode, node. This is the distance between antinode and node. Now suppose L is the length of air column, then the distance between, see, this distance is lambda 1 by 4. This distance is, see, this is the node, this is the node. The distance between two successive nodes, it is lambda by 2. It is lambda by 2. Now rearrange the equation or we get here, see, 3 lambda 1 by 4. Therefore, here we can write lambda 1 is equal to 4L by 3. We consider here the corrected length, that is 4L. It can be written as 4 into 4 by 3L. Now we have the formula N1 is equal to V upon lambda 1. Substitute here, we get V upon 4L by 3. We can write here N1 is equal to 3V divided by 4L, or we can write 3 divided by 3V divided by 4 into L plus E. Now see, this is the equation number 2, that is N1 is equal to 3V divided by 4L. This value contains the fundamental frequency, that is N1 is equal to, we can say it is 3N. This is the frequency of second mode. It is called as, see, N1 is equal to 3N, hence it is called as third harmonic. It is called as third harmonic. It is the frequency of third harmonic. It is also called as frequency of first Aher tone. Now we consider the next figure. Now in next mode, antinode is at the open end and node is at the close end. Now here we consider this is the incident wave and the wave is reflected forming a stationary wave. Here node, this is also node, this is node, this is antinode, antinode. Now L, it is the length of Aher column. In this mode, there are 3 antinode and 3 nodes. For this, in figure C, for figure C, the wavelengths are N2 and lambda 2. It is the frequency and wavelength of this mode. The length of Aher column, length of Aher column is equal to the successive distance, that is distance between antinode node, distance between node node, and distance between successive node. Now this is the distance, that is lambda 2 by 4. This is the distance between two successive node, it is lambda 2 by 2. The distance between successive node, it is lambda by 2. Now if we consider, we calculate this value, it becomes 5 lambda by 2 divided by 4. Therefore lambda 2 is equal to 4L divided by 5. Now here we consider with end correction and we get L is equal to 5 lambda by 2 divided by, substitute the value, that is lambda 2 is equal to 4L divided by 5. Now we know V is equal to N2 lambda 2. Substitute the value, that is N2 is equal to V upon lambda 2, that is V upon 4L divided by 5. It is 4L divided by 5, it is 5V divided by 4L, that is N2 is equal to 5V divided by 4 into L plus E or 0.3D. This is the equation, that is N2 is equal to 5N. Here this is the fundamental frequency, that is we can say that N2 is equal to 5N. This mode having the frequency 5N. Now in this case, this frequency is called as frequency of fifth harmonic. Frequency of fifth harmonic. It is the frequency for fifth harmonic and the frequency for second overtone. Second overtone. Now see, from equation first, from equation second and from equation third, the modes of vibration of Aher column consist of the frequency N, 3N, 5N, etc. That is, we can say that the frequencies are N, 3N, 5N, that is, these are the odd numbers. These are the odd number. Therefore, we can say that the vibration of Aher column in a pipe closed at one end consists of only odd harmonics. Odd harmonics. And the frequency is given by, it is 2p plus 1 into n. Here 1n, 3n, 5n, these are the odd numbers. Therefore, we can say that the vibration of Aher column in a pipe closed at one end consists of only odd harmonics. This is the frequency for first harmonic, this is the frequency for third harmonic, this is the frequency for fifth harmonic. Now this is the frequency for first overtone, this is the frequency for second overtone. Thank you.